Welcome to Futureproof Your Planet, our Sustainability Master Series, where we discuss how science, technology, engineering and fashion can help us improve our planet. I'm Esther, I'm a second year physics student and I'll be your host. Today I'm joined by Pete,
Hi.
Who'll be going over how in different ways in physics can be more sustainable, from dark energy to accelerators.
The climate crisis is here, and we are seeing ever more severe evidence of the negative impacts of human activities. As scientists, we have a responsibility to act. And here in the University of Manchester's Department of Physics and Astronomy, we take this responsibility very seriously. The challenge of limiting climate change and the degradation of delicate ecosystems is a multifaceted problem, but as physicists, we have a lot to give. This includes direct contributions to new technological advancements, the development of models and modeling techniques, and driving positive changes in the ways that we undertake our research activities to limit their negative environmental impacts. And this includes dedicated efforts to acknowledge the co-benefits, but also tensions that exist between achieving greater environmental sustainability and social justice. Next, you'll hear from colleagues about our work on sustainable computing for big science, on open data sharing, on the development of new technologies for heat pumps, and the development of more energy-efficient particle accelerators for applications in basic science and medicine. But this is only a snapshot of our contributions to international efforts to address this challenge.
Particle accelerators are used in some of the biggest experiments on the planet, with the Large Hadron Collider at CERN spanning 27 kilometers in circumference. While this means we can explore fundamental physics at the highest energies, it also means the field faces huge challenges in terms of sustainability. The largest linear accelerator in the UK is Clara at Daresbury National Laboratory, located just a short trip down the road from Manchester, and where our staff and students perform cutting-edge science, ranging from novel laser techniques to medical accelerators for cancer treatment. You can see the size and complexity of these machines, and as a result, they require tremendous amounts of power to run. Again, as an example, CERN itself accounts for a third of the energy consumption of the city of Geneva. They also require lots of materials such as concrete for X-ray shielding, which all contribute to a huge carbon footprint. At the University of Manchester, we are a partner of the Cockcroft Institute, the National Centre for Accelerator R&D, and one of our really exciting areas of research here is exploring novel concepts to make tiny particle accelerators, reducing their cost, materials, and energy requirements. One of the most promising concepts is the plasma wake field accelerator. Driven by high-power laser pulses, it can generate accelerating fields up to 1,000 times higher than conventional radio frequency accelerators. This makes it possible to produce high-energy giga-electron-volt particle beams in only a few centimeters. This drastic reduction in size has the potential to radically transform the future of particle acceleration, but there are still major challenges to solve to make this technology ready for real-world applications. And it's here at Manchester, with our team of research staff and students, where we work to solve these challenges and take the next steps towards a sustainable future.
Here in the University of Manchester, we're developing the next generation of heat pumps based on natural rubber. When a rubber band is quickly stretched, it gets hot. You can feel this by stretching it quickly and placing the rubber against your forehead. Similarly, when the applied strain is released, the rubber cools down. This is known as the elastocaloric effect and is related to the entropy of the polymer chains from which the rubber is made. When the rubber is stretched, the chains align and their entropy decreases, resulting in an increase in temperature. This heating and cooling cycle exhibited as you stretch and release is physically analogous to the refrigerant cycle that occurs in refrigerators, heat pumps, and air conditioning units. The problem with AC units and the like is that they use chemicals known as refrigerants, which have a global warming potential 1,000 times that of CO2. It might surprise you, but elastic bands and the renaissance of polymer elastocalorics could underpin the future of solid-state cooling technology, replacing conventional vapor compression refrigeration systems.
The nature of dark matter, which makes up 85% of the universe's matter content, remains a fundamental mystery. CERN and other research facilities are conducting experiments to detect dark matter, which requires extensive computing and storage resources. Now, a potential dark matter discovery will necessitate comparison with other experiments' results, and then an energy-efficient software for preserving and reproducing these physics results is crucial to minimize the carbon footprint of handling these large data sets. The Virtual Research Environment Platform, jointly designed by CERN and Particle Physics Laboratory Annecy, France, provides a computing cluster for full physics analysis using reanalysis software. It significantly reduces the need for dedicated computing resources and ensures access to the digital content in line with fair data principles. This platform aims to demonstrate how big data sciences can benefit from using common technologies. At the University of Manchester Experimental Particle Physics Department, we actively participate in dark matter searches within CERN's ATLAS experiment, and we have successfully integrated an ATLAS experimental analysis workflow into the Virtual Research Environment platform. This prototype test case allows other experiments to cross-check ATLAS results using shared resources. As part of our next steps, we plan to leverage cutting-edge machine learning and artificial intelligence techniques for potential groundbreaking dark matter discoveries. We plan to utilize the virtual research environment for complex machine learning workflows similar to those used by the big science experiment data analysis. And this aligns with the efforts towards net zero and global sustainability goals in the UK.
Answering some of the most challenging questions in modern physics relies on huge international collaborations. And the ATLAS experiment, which is a particle detector at the Large Hadron Collider at CERN, produces vast amounts of data from the particles produced and detected in high-energy particle collisions. And this data from the collisions is then calibrated, analyzed, and interpreted against our current best theories. And this is done in order to search for answers to questions about what our universe is made of, and the nature of the fundamental forces that govern the interactions between the matter. Now, precisely understanding the data from these collisions requires time-consuming and CPU-intensive data processing, and here we're talking about 25,000 terabytes per week. And it needs as well detailed simulations of the detector and its response to all possible particle interactions, along with years of work by physicists across the globe to understand this complex data and then be able to release new results. Now, what if in the future we want to test new theories, or if someone has a new idea? This is why we want to make sure that the effort and resources that go into processing and understanding this data don't have to be continuously repeated. It's for this reason that here in Manchester we play a central role in an open science initiative to publicly release and provide support for a large fraction of processed data from the ATLAS experiment. And in addition to the datasets, we also provide documentation, tools, and education material such that the users can understand the data and explore its full potential. Now, this enables greater transparency and reproducibility of scientific results, and allows as well for a wider participation in the exploration of this scientific research. This data is already being used in Manchester, in particular in public events and educational activities, and our undergraduates analyze this data to tackle their own research questions, and we are currently developing a new program to bring this data into schools to support physics and computer science. Beyond this, the public reuse of simulations and process data from CERN also allows for more science results to come from the same datasets, while at the same time having reduced energy demands. And by providing a greater access to scientific data to the worldwide community, we also allow for the development of new ideas that can improve the data analysis via more efficient, novel means, and this can enable potential future discoveries.
Members of our department have spotlighted examples of where environmental sustainability is a direct focus of our research, and examples of how we are embedding sustainability into the way that our research is undertaken. Our undergraduate physics course is informed by this world-leading research, and this includes the same theme of environmental sustainability, as well as associated issues of equity and inclusion. As a graduate of the University of Manchester Physics Programme, you'll be equipped with the skills needed to help build the green economy that our future depends upon. You will have acquired the quantitative and problem-solving skills that are highly prized in physics graduates, and you will have had the opportunity to complement these key physics competencies with courses on energy sources, data science, or various applied disciplines, as well as courses provided by our colleagues in the Department of Earth and Environmental Sciences, the School of Biological Sciences, and the Manchester Enterprise Centre on climate and energy, atmospheric physics and weather, meteorology and forecasting, biodiversity, or interdisciplinary sustainable development. You will have found undergraduate research projects on offer with varying focuses on sustainability, from projects aiming to ensure the climate resilience of basic science, to others with direct implications for climate mitigation. From there, a sustainable future is yours to build, and we will be proud to have championed you on your way.
Welcome back. Now we're going to do our Q&A section. So our first question is going to be, what is ATLAS?
So ATLAS is one of the general purpose detectors at the Large Hadron Collider. So there's 4 big experiments on the Large Hadron Collider, and one of those is ATLAS. It stands for Atoroidal Large Apparatus. So not the best acronym in the world, but it stands for this large general purpose detector. So you can do lots of physics with this one detector.
And so that detector, is that something that lots of different universities get to be able to work with, or is it just by CERN? Like, how do people get to use that? How do we get to use that data, essentially?
Absolutely, yeah. So the experiment itself was designed by thousands of people are on the ATLAS collaboration. So various parts of it were built by different universities all over the world, and then it was all assembled at CERN when the Large Hadron Collider was built. That data is it's a huge volume of data, which is all managed through the large worldwide computing system that CERN, that the Large Hadron Collider uses, and much of that data now actually is publicly accessible. So there's this huge program of open data, which is one of the things that's talked about in the video, and that's to make sure that the data that's produced through publicly funded research is available to the public, that it's not hidden behind paywalls.
Yeah. The next question is, data centers are growing multifold to store and manage data. What are your views on how to make them more sustainable?
Really good question, and there's huge challenges in terms of how to make these data-intensive sciences, where there's large requirements on compute, really make that much more energy efficient. And so what you're looking at with these big data centers, one of the big challenges is keeping that computing equipment cool. So you're looking at things like, well, how do we use less water to cool the computing? How can we implement the hardware in a way that means that it's more efficient? How can we power those data centers? Can we locate them nearer to renewable sources of energy, for instance? These are all big challenges. And one of the big things now is there's this aspect of climate mitigation. So what can we do to limit the effects of this computing that we're using? But now as well, we have to consider the sort of climate adaptation aspect, that if you want to keep computing cool, then you can't do that if outside it's really hot, because you need temperature gradients in order to be able to cool things. So that's increasingly a challenge as well. So people are trying to find new ways of cooling data centers to ensure that, well, they work, but also that it's done in an energy efficient way.
In the video you mentioned about how there's different projects that students who study physics can do to work on sustainability. Could you go into more detail about what those are?
Yeah, sure. So one of the really great parts about the physics program at Manchester are the BSc dissertations and the MPhys projects in the 4th year, if you do the 4th year. And there you really get to do a little bit of research, where you get to look in more detail at a particular research topic. And there we run projects that are linked to sustainability. So it might be new ways of implementing software and codes so that they're more efficient, that they use less CPU time. It could be ways of designing experimental infrastructure in a way that's much more environmentally sustainable. It could be work on this framework of life cycle assessment. So the idea that when you build an experiment, from sort of thinking about what that design will be all the way through to dismantling and decommissioning that experiment, you work out at all stages what the environmental implications will be, what things you're putting out into the environment, what the energy usage is, and then you can use that as a process to optimize the design of experiments. And that's also something that students in the past have been involved with.
Yeah. How big of a part do you think developments in nuclear fusion energy will play towards the goal of net zero in the next century?
Very good question. I think one of the things that one has to really bear in mind are the timescales of all the types of mitigations that we might want to put in place. And I think it's probably safe to say that we need a whole landscape of mitigations coming in order to achieve what we want to in terms of reducing emissions and moving away from carbon-intensive sources of energy. So any progress that can be made on any front is welcome. But in the big picture, we need move towards more renewables. We need other ways of managing the grid, ensuring stabilized grids and multiple ways of generating that energy and storing that energy in a way that's environmentally sustainable.
The next question is, how best can we encourage the genuine consideration of long-term sustainable goals?
I mean, this is a really important question, and I think cuts across all disciplines. It's not just a physics question, and it really relies on a system-wide way of thinking, a systems approach where you take into account all of the aspects and challenges associated with environmental sustainability. So environmental sustainability is a technical challenge on one side, but it's also a human challenge on the other, and you've got to pull together those social aspects, the psychological aspects, the economic aspects, and the technical aspects in order to achieve that. So sort of joined up thinking, system-wide change, looking at the incentives that are in place and how those might be, for instance, perverse incentives that actually drive things away from environmental sustainability, and thinking about all of that in the whole is really what we need to do to make progress, I think.
What would you recommend for a student who would want to come in and study physics at the university? Like, what should they look into?
Another really great question. I think, I mean, the first thing I would say is you really want to be doing something that you're interested in, right? You're going to commit lots of time to it, and you want to be making sure that you're going to enjoy it and you're going to engage with it and get what you want out of that program. If you're really interested in physics, then start reading, looking around at things, and finding out what areas it is that you're interested in. That would be my advice.
And after the degree, what career paths of specialisation are there, and what advice would you be to trying to go into a certain path?
Another really great question. I think as a physicist, you learn really a lot of useful analytic skills. So you have that ability with mathematics, you're able to abstractify problems, and you have a lot of tools that you learn in how to solve problems, and that's a really valuable skill that can be used across many sectors. So there are lots and lots of sectors that employ physicists, everything from sort of data analytics through to teaching and onwards. There's a huge variety of careers that physicists go into where they can make use of those analytical skills, those problem solving skills.
This will be our final question. How can students at the university be more involved in sustainability? Can't talk now.
Yeah, so I think there's lots of things going on at the university. There's lots of things within the physics department that you can get involved in. We have programs of summer internships as well, for instance, where students can do work within research groups, and they often, many of them are sustainability related. So there's all these different opportunities to engage with things. There's things across campus. The university has a huge social responsibility agenda, and they organise a great deal of events and actions that you can get involved with.
Thank you so much. Thank you, Pete. If you guys have any more questions, you can leave them in the comment section, and we'll try to get to them. Next Monday, we have our final talk, which will be about civil engineering. So you can join about that and see how that can be more sustainable. Thank you.
Thanks, everyone.